I'm always looking for new and better methods for my archiving workflows, and one area I've never expanded upon has been optical disk ripping. Up until now, I've just used the drives in my computers or USB drives, but I've always had my eye on disk changers. In 2017, I did a video on the NEC slot loading changer, and in 2022, I did a video on the Torsen caddy changer, but those were never the end goal, just a fun step along the way. Some things I haven't made videos on are these Pioneer DRM 6324X and 1804X jukebox changers. These take these 6 disc caddies from Pioneer's home stereo line and let you work with many more discs at once. But the reason I've never made a video about them is that they don't allow full access to the discs and are completely unsuitable for ripping. But I have known what the real answer was for years. Disc duplicators. A whole product segment dedicated to high throughput CD and DVD work, though for writing, not reading. I managed to find an example of the most common variety of these locally, but that's just the tip of the iceberg. The next style is one of these, a hopper-based solution that can drop discs down from above. But even that can be bested. This is a 3-drive, 3-hopper, robotic disk duplicator, capable of queuing up to 200 disks and working with 3 of them at a time. This is my dream machine for disk ripping, but it had many problems. There was no documentation on how to use this thing, and the CD drives in it failed one of my tests to be suitable for archival ripping. So I had to completely reverse engineer the software interface and modify the unit with new drives. Sounds easy, right? Well, this took about a month of non-stop work, so buckle up while I walk you through why you should never get one of these, but why it's so awesome and you'll want one anyway. First, let's go over what these actually are. This is an Aleratec RoboRacer LS, and this is the kind of changer you should want, except this one kind of sucks too. The other is an Aleratec Autopublisher LS, and for completeness, this first one is a generic copier, but what piqued my interest, aside from the Plextor drives, is its claim to do CD plus G, something I will test in a future video. But both of these machines were also available as an SA model. The difference is that the LS units are controlled by software over USB, and SA units are standalone. Keep in mind, these are meant to act as duplicators. They're advertised as being able to write disks for low to medium volume publishing, so it'd be an advantage for the standalone models to be able to write disks without a computer, but they also typically weren't meant to connect to computers. These LS models are far easier to use for ripping as a result. Now, I got both of these units at once, but frankly, if I'd only bought the RoboRacer before the Autopublisher, I would be happy. Its hopper holds up to 50 disks and uses a simple sliding tab to push one disk through at a time. The disks fall down a set of rails and land into the drive tray. Then you just close the tray normally and work on the disk. Ejecting is where this one gets weird though. There is an arm underneath of the tray that can move up and down. This arm actually holds the tray up, and when it lowers, you'll see the tray is hinged and the disk is able to fall to the side and land in a bin. This makes the tray in this drive unique because it must have that hinge in order to work. This would be fine, except the Lite-On drive in this fails my first test for being archive capable too, but we'll get to that later with the other machine. For now, I haven't covered how you actually use this thing. The unit has a USB IDE adapter to connect to the drive and a USB serial adapter for the interface. They are connected internally through a hub chip with a single USB port for both. Connecting it to a computer has it show up as a normal disk drive and a serial port. The machine accepts commands over serial to perform the different actions it can do. Thankfully, this machine has already been documented online and all of the commands I needed were available right here. Really, there are just 3 commands you need. Kick down the next disk, arm up, and arm down. With just those, you can do everything you need. And I've been working on the perfect solution for integrating these kinds of commands into my ripping workflow. I have been writing my own modular media archive tool to handle automated ripping and decoding of data from different sources. If you want to know more about this software, I've made a video going about it into more detail on my second channel. Since that video, I've been working on a web interface that allows you to queue up sources to rip and manages going through them. Now, integrating a disk changer into this was always one of my goals. I added a concept of controllers to my software to handle this. When a sample's load or eject action is called, if a controller is assigned, then it defers to that. This is where the changer's commands are sent for loading and unloading. Controllers are enabled in a settings file that you provide when you start the software and assigned to the drives that you set up. So all I have to do to use the RoboRacer now is to define its drive and associate its controller with it. Now I can load disks into the hopper and start queuing them up for ripping. It will automatically drop them in, close the tray, and start the rip. When it's done, the arm is lowered and it ejects the tray that will drop the disk into the bin. Now this is very definitely the abridged version of how I got this thing working, but the other changer proved to be so much more work that we're going to be talking a lot more about it. But I'll say that this machine is way easier to use and works super well. If it weren't for the drive, it would be the easiest recommendation for an automated ripping solution ever. Now there are similar models from other brands with a different loading mechanism that might work better, but I don't have those. So instead, it's time to talk about the big one. This is the Aleratec Autopublisher LS. It uses an arm with a clamp to grab disks and deposit them into the trays of the 3 drives it has. Like the RoboRacer, this is meant to act as a duplicator. Now as an aside, I actually find it a little funny how both units push LightScribe so much on their boxes, because it's kind of a terrible way to label your disks for consumer use. They provided the driver disk for both of these units on LightScribe disks, and they look expectedly meh. There were changer duplicators that integrated full color printers instead, which would look so much more professional. Speaking of the driver disks though, I didn't talk about the driver disk for the RoboRacer because they kinda screwed up and didn't put any software on the disk. It's just a PDF of the manual. The Autopublisher's disk does come with the original software though, which is a really good thing because it is the only known copy of something that can interface with this machine. Or at least it was. Unlike the RoboRacer, there was no information online about the commands to control this machine. It works in the same way with USB IDE adapters and a USB serial interface on an internal hub. But this is only ever meant to be used with the original software though, which is Dropix Recorder XE. This is a program specifically for bulk disk writing and controlling robots like this. This is a somewhat limited version though, that only comes with the driver for this Aleratec robot though. To use it, you have to set up the drives and then calibrate the robot. After this, you can run a test and see the robot perform a full load and unload cycle. And this is the most I've ever used this software. I'm not interested in writing disks, but I am interested in how it works. The driver turned out to be a single DLL that I was able to easily extract the strings from. There was a lot of garbage to sift through, but after working on the RoboRacer, these lines stood out to me as likely being commands because they followed a similar structure. This let me know what I would probably be looking out for as far as how to control the robot directly, but that wasn't that useful on its own without knowing what the commands do. Now I'd put this DLL up on my Discord server as well, and some of my viewers there started trying to reverse engineer it more directly. They found some info in there related to the commands that gave us an idea what they do, but it was a little confusing and far from the complete picture. That wasn't the method I wanted to use though. I've been running the original software in a VM on a modern computer for a reason. With this method, I could intercept the transmitted data from the host OS and see everything the original software does. To accomplish this, I'm using Wireshark on Ubuntu. After setting up USB redirecting, you can use LS USB to see what bus a particular device is on. Then you can start monitoring that bus for USB traffic and look for data sent to or from that device. With that ready, I ran the robot test and was able to see the commands sent to the robot. These were the commands it sent to do that. Now I took a bit of a safe guess that the 3 big motions that it does are related to the 3 larger commands. First, some kind of check on the drive, then it loads a disk, and finally, it unloads a disk. We can deduce a bit more from this though. It unloads a disk from drive 1 to bin 3, and it loads a disk from bin 1 to drive 1. This tells us the packet structure has a command indicated by the C group, then 2 data groups behind D and N. The C1 and C2 commands here weren't as obvious though, but from the DLL we had a hint that they could be something like cancel command, clear alarm, and home. This was the beginning of the process that I would be using for reverse engineering this thing, but that was far from the end of making it work. The next problem was initializing the machine. When I went to try and send commands back to the robot to see what they did, it worked. The first day. The second day, it didn't work at all. I left out that when first connecting to the robot, I logged the software sending these commands, but they didn't seem to be working later. Now around this time, I ended up changing from using Wireshark on the Linux side to Portmon inside the VM, which was easier to see the commands and responses. More importantly though, it also showed me how the serial port was being configured by the software, which was kind of confusing. In the end, it wound up just being 9600 baud, 8 data bits, even parity, and 1 stop bit. And I'm getting ahead here, but DTR had to be held low when connecting over USB, but not when directly connecting over serial. After that, I reran the logging with the software and found it sent way more commands that time. I had theorized that the robot would store its calibration data and recall it with the original commands, but after seeing the wall of data it was sent, it was clear I was getting all of the calibration data from the software and was replying somehow that it was already calibrated on subsequent queries. The response to C8, D9, and 2 specifically seemed to indicate the calibration state. I modified my work in progress software and was able to send it back all of the calibration data directly and was able to start controlling it from a cold start now. From there, I went to work on figuring out what all of the other commands do. I began documenting everything I found on my wiki, and there is now a very complete documentation of how to control it. This took a lot of work and trial and error to do. There are a lot of complex elements to this. Every command gives you a status response that indicates errors in machine state. This is useful for adding smarter logic. Like my software will detect that no disk was found on a load command, it will automatically try the next bin, which allows for adding more disks to the queue while it continues to work. This technically means that it can rip for an indefinite amount of time as well, but the RoboRacer can do the same thing in a much less complicated way. Now I'm not going to go over all of the commands and calibration properties because this thing is insane. There are other robots like this, made by other companies, and from what I can see, they are all drastically less complicated. After all of this, I was actually able to take the logic for my robot and dumb it down to work with a generic command set that enabled my software to work with a disk robot that one of my supporters has. Thank you, Matrox Millennium, for trying this out and getting me some footage of it working. It is so cool to see this being useful for other people. But that machine has commands like I and A, so that took like 2 hours to implement. My machine is way over-engineered. For example, there are 2 unload commands. C4 is the normal one, and the other, C10, is identical, except when it raises the arm, it waits slightly longer before moving back down again. This is meant specifically for putting the disks on the reject spindle, which is down here, and technically bin 5. The delay is to give the drive trays time to close. My machine also allows you to fully control the arm, which allows for custom movements. But no, it doesn't let you drop a disk while moving, so you can't make a throw command. I was very disappointed. Now I've also figured out a lot of the calibration values, but that didn't matter too much yet. It mattered a lot more though once I changed the drives. Okay, so now let's go over the drives in both the RoboRacer and the Autopublisher. These drives are made by Lydon, and like I mentioned earlier, I rejected them for archival purposes. My main test for this right now is the album Factory Showroom by They Might Be Giants. This CD has a hidden track before track 1. On a normal CD player, you can access this by starting track 1 and then rewinding into negative time. This is easy for most CD players, but very difficult for a lot of CD-ROM drives. Most of them will refuse to read data outside of the regions in the table of contents. This includes these Lydon drives. Attempting to read before track 1 will throw interface errors with the drive. So I don't want to use these, and that's why it's a shame that the RoboRacer's drive is unique. I use this particular test because if a drive can read that far out of the talk, it probably doesn't have too many limits and will be better off for reading more complicated CDs. This isn't the video to get into the complexities of CD ripping, but it's awful. Now, to make a long story short, I'm using Asus DRW24B1ST drives, and they can read the hidden track. I owned 2 of these before this project and bought a 3rd to complete this machine. This drive isn't on any of the compatibility lists for the big CD archiving projects yet, which is why I went with it. It's still affordable, and since I needed 3 identical drives, it wasn't financially crippling to get them. Also importantly, it is a CD and DVD drive, so I can throw almost anything in there and be just fine. I'm skipping Blu-ray because that media varies a lot more by platform and is usually not suited to bulk ripping like this anyway. So this is about the perfect setup. At least it is now. While these drives are technically fantastic, the implementation of them in this application was a complete nightmare. But before I can even get into that, there's a bigger problem to solve. You know how I mentioned that there are USB IDE adapters in these robots? Well, the ASUS drives are SATA. And inside the robot, we can find this very custom board that is very much only ever going to be IDE. I needed to make some changes, but I was okay with that. Switching to SATA was always my plan. Mostly though, because I also wanted to switch the internal hub to a USB 3.0 one to be certain that I was never going to run into bandwidth limits while ripping. Generally, while writing disks like this was made for, slower was better, so the speed of the disk access was never really an issue. But for reading, we can go a lot faster. These ASUS drives are capable of 48 times speed CD reading. That's 7.2 megabytes per second. All 3 running at once would be roughly 21 megabytes per second. USB 2.0 is theoretically 480 megabits per second or 60 megabytes per second. So that should be safe, right? Well, have you ever seen a USB 2.0 device hit those speeds? Because I sure haven't. And here's a great and simple QA page from Microchip on why. TLDR, you can expect to see about 35 megabytes per second max because of the packet structure and driver overhead. And we can kind of confirm this by looking at the Wireshark captures from the serial commands. The actual data of the USB packet is a small percentage of the total of what is sent. So that 21 megabytes per second for all 3 drives would most likely be constrained by the USB 2.0 bus, considering all of the overhead. And I probably should have just led with this, but if I'm ripping 3 DVDs, these drives could reach over 66 megabytes per second, exceeding even the theoretical speeds of USB 2.0. So going USB 3.0 and SATA just makes sense here. Now I could just build a pie into this with a PCIe SATA hat, but that really limits how this could be used. So I was determined to keep the USB connectivity while upgrading it. I decided on a very particular setup. I found a 4-port USB 3.0 hub that specifically had a female USB-C data connector on it, and also supported power injection, though power injection would be far more important than I knew. I was then going to use a USB-C panel connector to allow connecting to the hub with an external cable. So that solved the USB data. Now for SATA. I bought 3 of these USB 3.0 SATA adapters that were very low profile, so I could install them in the back of the drive cage without having to worry about space. They also have external 12 volt, which I plan to tap from the ATX PSU in the Autopublisher. So far, so good. Well, not quite. One of the USB adapters that I bought was DOA. That sucked, but I got a replacement on the way and used a different adapter that I already had on hand in the meantime. This was delay number 1 on this project. I wanted to be smart about this and decided to test everything outside of the robot first. And during that, I was having considerable trouble getting all of the drives to work consistently. I was working on this live and it was pointed out to me that SATA optical drives used a lot of 5-volt power. I figured it couldn't be that much until I flipped over one of the ASUS drives and saw it uses a cool 2.5 amps of 5-volt DC. Even USB 3.0 is only rated for 900 milliamps. So I tested the 5-volt rail of the hub and found that it was drooping all the way down to 4 volts before even my meter gave up and shut down. So that wasn't going to work with these kind of SATA adapters. That Pi option is starting to look a lot more appealing. I needed a solution for SATA data only without power, and basically anytime you search for USB SATA adapters, they always come with power. Now, I know that these exist, but this is just a PCIe USB bridge to an M.2 SATA controller, and as a Linux user, I've learned not to trust 5-port SATA controllers. It doesn't matter anyway though, because one of my viewers, thanks again Helen Croft, came in clutch and found the perfect single-port data-only SATA to USB 3.0 adapter. I ordered 3 of those, and then had to wait. This was delay number 2 for this project. After getting the new SATA adapters in, another was DOA. Seriously, I can't make this up. I opted not to get a replacement this time though, because These have a new problem. They don't fit in the hub. Even shocked. I was buying another thing for this project though, and since one of these adapters was dead anyway, I figured I still have the USB powered ones, and one drive at a time, it did actually work with those. So I used a mix of adapters which let me fit everything I need. I also ended up making a custom adapter cable from Molex to USB-C and 5.5mm barrel jack to power the hub and the drive adapter. Which brings me to this. Bask in the glorious spaghetti mess to make all of this work. In that mess is also a USB serial adapter because I needed to replace the onboard one as well. It turned out that internally, the robot had a DE9 serial port anyway, so that was very easy. That made me realize that the rear panel was actually 50-pin Centronic sized as well, so I bet there are older models of this system out there with DE9 serial and SCSI drive connections instead. Anyway, at this point, I was really wanting this project to be over, so I used the clamp on the hub I got, which is meant to go on the edge of a desk, and just squeezed it onto the serial port of the board that I had now disconnected. Not my finest work, but I was trying to get this video done and tired of delaying it. I ran all of the cables I needed up into the drive cage and popped in all the ASUS drives. At this point, I took a moment to make a few simpler mods as well. The reject spindle just drops the discs onto the metal top. I may use this for discs that I want to mark for deeper rip attempts later, but I don't want to scratch them, so I put some soft pads down around it. I also cut some of the pads to put on the doors because they mount fairly loosely and rattle a lot. This dampened them and made the unit much quieter. With that, it was all together now, and I could try the ASUS drives in it for the first time. I knew I would need to calibrate the robot though because the drive trays would be in different positions, but I wasn't prepared for how difficult this would be. Actually, it's impossible, but figuring that out and solving it was a whole other problem, and this was the third and largest delay to this video. ASUS very clearly designed these drives specifically not to be usable in a robot like this. There are at least 3 different design choices they made that were all completely unnecessary, except to make these unusable for this. First though, I need to talk some more about the calibration features that this robot has. When it goes to place a disk on the tray, you'll notice it drops down in front, then slowly moves towards the drive again and releasing the disk. It does the same motion in reverse when removing a disk. The original software described this motion as the short tray setting and gave you some drop-down options for how to handle it. It's meant to account for drives that don't fully move the tray away from the drive bezel, where the disk might hit the bezel. Now, the original software doesn't expose this calibration anywhere near as openly as it actually is. After reverse engineering more of the commands, I know you can calibrate the height it stops at over the tray for both loading and unloading separately, the distance that it slides the disk across, and tangentially related, the exact vertical position of all 3 drive trays. The original software only lets you calibrate the top one and then just guesses for the other 2. Now, at first, I didn't think I would need all of these short tray settings, but it turns out that they are vital for these ASUS drives. I'm gonna hide the first problem I found for now, but a problem that stemmed from it was needing to get the short tray working, because these drives don't eject the tray out far enough for the disk to be able to be pulled straight up. This means that we need the wiggle motion to get the disk in or out. But there's an extra fun problem related to this. The door on the tray is extremely close to the disk. It's actually so close that there isn't physically enough room for the disk to be removed while level. ASUS designed this drive so that the user must slightly angle the disk as they take it out. This was imperceptible before I'd put it in the robot, but once I started calibrating for these drives, it became painfully obvious. So the first thing I had to do was remove the drive doors. That's why they've been missing in this video, and I'm actually showing some spare drives that have them on still. But even that wasn't enough. After removing the door, you still can't move the disk in and out while level, because there is a lip in the seal for the tray door that sticks down. Now, I could have easily removed the drive bezels completely, but I didn't want a bunch of dust getting inside. So I dremeled off that top lip on all 3 drives. This allows the short tray motion to have the clearance to lower the disk in place. So now it works, right? Well, after I made those mods, I attempted to let it run through a set of test disks, and it was going great until... What just happened? Well, let's go back to the first problem I found. First, let's eject a disk from the drive like normal. Take note of the silver mark on the tray though, because if I now close the tray and just reopen it, The tray sticks out more than it did before. Let me say that again. The tray ejects from the drive different distances when it does or does not have a disk in it. The only reason I can think of to possibly do this is to make using it with robots like this impossible. It's purely an antagonistic feature. And no, vertical orientations don't excuse this either, because it would have to short eject the tray when empty as well to be able to hold the disk in when loading like that. Now, the drive uses reading the disk as the detection mechanism for this. There is no sensor that we can fool to make it think there is always or never a disk in the drive. But as evil as that is, I was originally tolerant of this problem though. I carefully calibrated the robot to drop the disk just barely far enough in for the short tray position to work, but they would also sloppily drop slightly on top of an empty tray and fall into place when closing the door. After the first disks are loaded, when doing a bulk rip job, the tray position should always be the same, since the drives will always have a disk in them when they open. So the problem is solved, right? That brings us back to this. I don't know what happened here, but the drive ejected out the full distance despite there being a disk in there. The arm attempted to pick up the disk from the short tray position, but that's not where it was, and the system jammed. This made these drives unpredictable because there was no way to determine where the tray is to have the arm pick it up from a different spot. I was about ready to just scrap the whole thing after all of the other mods I had to do, amounting to nothing now. But I had one more idea of how I could solve it. But first, I needed to open the drives. I had noticed that when the drive trays are fully open, they hard stop. They are being physically limited, not with a sensor. But with a disk in the tray, they can still be manually pulled out just a little more. I wanted to see what this looked like inside, and with the case off, at least the full stop travel position was obvious. There are tabs on both sides of the tray that run into the case and positively stop it. So I opened another drive after it was ejected with a disk, being careful not to move the tray, and found that it stopped right before this opening next to one of the stops on one side. My best guess is that this blue switch under the tray that is actuated by the tray gearing is how it knows it's in this position. This is probably also the same switch that lets you push the tray back in to close the drive. Now I think trying to defeat this switch and getting the tray to always fully extend is a fool's errand. But the only thing I really need is consistency. So going back to the positive stop, I wondered, could I make it stop without a disk in the tray in the same position that it stops with a disk? And the answer is yes. Once it hits a stop, even if it's shorter than normal, it works just fine. And I instantly knew what I wanted to do. That opening beside the drive tray stop, I wanted to design and 3D print a part to fit in there to extend the stop location inside the drive. It took 3 revisions to nail the exact stop position, but this ended up being absolutely perfect. I installed the stops in all 3 drives, and that finally made the drives usable with this setup. They now always open to the exact same position, and I can load and unload the disks cleanly. I have had to do so many mods and exceptions that I'm still expecting to have to iron out bugs on this thing, but it finally passed my rip test flawlessly and is working exactly as it should. So I might be in the clear. So now that it's fully working, let me walk you through how I can use this machine. Let's rip the soundtracks for Breath of the Wild and Tears of the Kingdom. 14 discs total. For my software, we set this up exactly the same as the RoboRacer by defining a controller and assigning drives to it. You also need to specify the order of the drives for the controller though. I also have some options for the groups and a FIFO that I'll set up for now, but talk about more when we get started. Now, to prep for ripping, I just need to load all of the discs. I'm going to reverse stack these, starting with Tears of the Kingdom's last disc, so we can go completely in chronological order. Now, I get the software up and running, it calibrates and initializes the robot, I add the hopper with the discs to the machine, and we're ready to go. Now, I do have a backend option for providing a single file with all of your media information at once, so you can predefine something like this. But I'm just going to manually add them through the web interface this time for visual reasons. All I have to do here is enter a name for the output folder and optionally a description. As I'm adding these, you can see the robot grab the disks for them and start ripping. And once I've typed in all of the basic info for the 14 disks, it's completely automated. And now we can see the groups and FIFO features in action. For any set of drives, my software can have them put into a group. And when you input your media sample info, you can either specify a specific drive to rip with or a group. When you use a group, it will find any available drive in that group to load the next sample into. This lets software track and manage the optimal use of the 3 drives as needed. But CDs don't all rip at the same speed, or for the same amount of time. So disk 2 or 3 in a set could finish before disk 1. And if the robot removed those disks first, the order of the output stack would now be different from the order of the input stack. So there's the FIFO option, or first in, first out, which tells later samples to wait to eject until all previous samples have finished. This is important because it makes the manual process of recasing all of the disks after much easier, because it's the same order, just reversed. Lastly, if I've already started ripping and I want to add a new sample, I can just put it into the next bin counterclockwise. When it reaches the bottom of the first bin, it will remember that it is empty and move to the next bin to continue. So I can keep adding more samples and let it work without stopping. I'm also planning on adding an option to add the sample to the front of the list for robots that don't have multiple loading bins like this though. But with that, the Autopublisher LS is now finally ready to be put into service as a disk ripping monster. As much as a pain in the butt it has been to get it working, really glad I did get this unit over any other arm changer. Using these ASUS drives in a robot like this that you cannot fully calibrate would be impossible. It's only thanks to the short tray features that I'm able to defeat ASUS. So, while it pains me to say this, after all of the trouble this thing caused me, I think this might be one of the best options for a bulk ripping robot. That makes it all the more surprising though that no one else has tried to reverse engineer one of these. Now, I still think that the top loading models are probably the better overall option though. They're just so much simpler, and as long as you get one that doesn't have the stupid drive tray, they're probably a lot easier to modify with a better drive. Well, that's going to be it for now. I've got a lot of disk ripping ahead of me now that I can queue up as many media samples as I want, let the robot do the job for me. If you enjoyed this video, you may want to subscribe because I know I'll talk more about CD ripping in the future. If you want to help support the channel, you can find me on Patreon. But for now, that's it, and I will see you next time.